We're going to try a new video capture software today, so please bear with me if we run into any issues. We're going to talk through the notes for lesson 8.1.1, which focuses on what is a polygon. So a polygon is a closed figure. That means it has no gaps or holes. And it's a two-dimensional figure. So it's a closed 2D figure made of non-intersecting straight line segments that are connected end to end. So pay attention to these words. Non-intersecting. That means our segments cannot cross. So for example, this is not a polygon, okay? Because the segments cross and they have to be straight lines. So something like this, like a semicircle, is not considered a polygon either because it has a curve to it. And if a figure is open, so for example, if you have something like that, that is not considered a polygon either because it is not closed, okay? So it is a closed two-dimensional figure made of non-intersecting straight line segments connected end to end. We can name polygons according to the number of sides that they have. And these charts here show you the names of specific polygons according to the number of sides up through a polygon that has 11 sides. So if it has 5 sides, we call it a pentagon. If it has 9 sides, we call it a nonagon. 11 sides, we would call it an 11gon. Really, anything after 10 sides, we just call it an n-gon. So the number of sides, and then we tack on the word gon. If a polygon had 21 sides, we would call it a 21gon. All right. We can also label polygons as being convex and non-convex. In a convex polygon, all of the shape's vertices point outwards versus towards the center, okay? So we say that the polygon is not caved in. Versus a non-convex polygon that has one or more vertices that point towards the polygon's center. So non-convex polygons, we say that they are dented. They are dented in some way, okay? And so if you notice, see, take a look at this polygon right here. Notice all of its dents, like right there and right there. This star has a few dents versus all of these polygons on the left, their vertices all point outwards from the center. So let's keep in mind those parts of the definition of a polygon and how we classify them as convex or non-convex. And let's talk through a few shapes here and decide whether or not they're polygons and if they would be convex or non-convex. This first one right here is curved. Polygons are not curved, so this is not a polygon. Okay? This one right here would be a polygon. Second one, part B, okay? Because it is a closed figure, it is made up of straight line segments and none of those segments overlap and it has no curves. Now the question is this convex or non-convex? Notice how every single vertex points outwards from the center. That makes it convex. Okay. For this one right here, I want you to pay attention to a part like that where the lines cross each other. That can't happen if we're talking about a polygon. So that one would not be a polygon. Okay. In part D, we do have a polygon. No curves, no intersecting lines. It's a closed two-dimensional figure, so it's a polygon. But notice this one has a dent. So this one is going to be non-convex. For this one right here, again, we have lines crossing. That's a problem. So this is not a polygon. But for this star, we actually had that picture as an example of a polygon on the other page. This would be a polygon. Again, no curves. We don't have intersecting lines. It's a two-dimensional closed figure. So that would be a polygon. And if you notice, it has several dents. So this one is non-convex. Okay. In G, we have a four-sided quadrilateral. Actually, this one is a trapezoid. And so this one would be a polygon. Again, no intersecting lines, two-dimensional, closed figure. All the lines are straight. We have no curves, okay? And this one would be convex. We have no dents, all right? And the problem here with this one is it's not closed. So this one would not be a polygon. This next set of problems focuses on a property of a specific type of polygon, the triangle, and it has to do with a relationship between some angles outside of the triangle and angles inside of the triangle. So I'm going to give you guys a minute right now to solve for x in each of these figures. Here's a little hint for you. You're going to be using some linear pairs here. Okay, like right there. You're going to be using triangle sum to help you out. For example, in this first triangle, you could figure out the measure of that angle inside of the triangle, okay? Or sometimes, like in this one, maybe you'll be using linear pairs first to figure out a second angle in the triangle to help you solve for x. So I want you to pause the video right now, work through this, and then we'll come back together. I'll share the answers for you, with you for what x is, and then we'll talk about a possible relationship between the angles outside of the triangle and the angles inside of the triangle. Okay, I'm going to put the answers up now for you guys. For this first one, you should have found that x was equal to 110 degrees. For the second one, you should have found that x was equal to 70 degrees. For part C, x is equal to 48 degrees. And for part D, x is equal to 108 degrees. All right, now here's what I'd like to take a look at with you. Take a look in this first triangle here. I'm going to call this third angle in the triangle angle Y. All right, and think about the relationships we know in this triangle. First of all, we know because of triangle sum that 35 degrees plus 75 degrees plus y is supposed to equal 180 degrees. All of the angles in the triangle should add up to 180. But we also have this relationship right here. We have a linear pair. We have supplementary angles. Okay, and we also know that if we take the measure of angle x and add it to the measure of angle y, we should get 180 degrees. Well, if we're adding quantities together and we end up in the same place, there's got to be a connection between them. So take a look at this, okay? We're adding these together. Both of these equations share y, which means if we're adding 2y in both cases, 35 plus 75 must have the same value as x if we're going to end up at 180, okay? Take a look at part C down below. Let me switch my pens here so I can write again. Again, I'm going to call this little angle right here inside of the triangle angle Y. And let's take a look at the different relationships that we know exist. We know that if we take the measure of angle X plus 100 plus Y, we should get 180 degrees because of triangle sum, okay? We also know because of this linear pair right there that if we take 148 degrees and add to it the measure of angle y, we should also get 180 degrees. Okay, so by that same line of reasoning, in both cases, we're taking angle y and we're adding something to it and we're ending up at 180 degrees. That something in both cases has to have the same value. So x plus 100 must be the same value as 148 degrees. Okay? And so there's a pattern, and if we took a look at triangles B and D, we would see that same pattern. We can model that same idea, okay? And so every time what we're doing is we're taking these remote interior angles, okay? That's what those are called. So in A, the 75-degree angle and the 35-degree angle, those are your remote interior angles. In B, X and this angle right here are your remote interior angles, okay? In C, angle X and angle 100 are your remote interior angles to the exterior angle that we're showing, okay? So here's your exterior angle. Your remote interior angles are the two that aren't connected with it in a linear pair, okay? And the connection is that every single time the exterior angle, its measure is equal to the sum of the remote interior angles. Okay, so what's a rule or formula we could write to demonstrate this? Well, in terms of our picture that we have right here, the measure of angle X should be equal to the measure of angle A plus the measure of angle B. Okay, and again, the reason for that is because we know that A plus B plus C should equal 180 degrees because of triangle sum, but also because of this linear pair right here, we know that the measure of angle X plus the measure of angle C should also equal 180 degrees, okay? And because we're taking angle C each time and adding to it a quantity and ending up at 180, that quantity in both cases must be equal to each other. C plus X or C plus A plus B. A plus B must have the same value as X. Okay, feel free to shoot me an email if you guys have any questions. I'm going to be posting soon the notes for sections 8.1.2 and 8.1.3.